In this video, we'll demonstrate the 2.1 cylinder flow tutorial. This is a brief demonstration for the workflow. Open TransAT and use the Create Project button, defining a directory. And a project name. It's important to define a unique directory and unique project name so that different projects don't become overwritten. Save, and we're first brought to the Mesh and BCs tab. For this problem, we have a geometry. We can use the Create Shape feature to create very simple geometries. We want a cylinder with the following initial coordinates: radius, length, and refinement for the GTS object. Then create. Once we click on the object, we can apply transformations, such as rotation, around the y-axis by 90 degrees. Then we'll also translate the object by the dimensions to a new location. Then, in our view, the object has disappeared, but we can reset the view. Then, we have our object prepared. With it still clicked, we can use the button Export to Mesh. We bring up either units, or we could define a custom scaling factor. But for this object, it's fine to leave in the default units of meters. Then we'll be asked if we want to resize the domain. We should also do this so that the mesh is put around the object. Now we go to our objects. We can see it has been input into the mesh. And also within this tab, we could define some properties. However, we can leave it as default. Realize the immersed surfaces are more options for advanced features. And the invert fluid solid domain can choose whether the CAD file is an obstruction, or if it's blue, it's a fluid flow. In this case, it should be an obstruction. For the Mesh and BCs tab, we'll define a size around the cylinder, where we keep most of the mesh behind the cylinder in the flow direction, with enough dimensions around either side. Since this will be a 2D problem, we choose a small dimension in the Z direction. For now, this is just a template, and we'll set up different meshes later. But to highlight one thing, we want to have discretized 2 in the Z direction. This creates only one cell in the Z direction for our 2D problem in X and Y. Additionally, the blocks will be set up later, and the BCs can be set up now. We will have an inflow and an outflow. The inflow will be set with a constant velocity of 0.015 meters per second. And the properties for our outflow should be set as a pressure as 0 pascals. Keep in mind the pressure is relative, so can be set as 0. Then on the inflow, we'll set the X min boundary. Because the interesting flow happens behind the cylinder, the inflow is on the closest surface to the cylinder, whereas the outflow is on the opposite end. For the 2D problem, we can set either side as symmetry. This keeps the flow parallel with that surface and applies a no-slip condition, or does not affect the velocity. Since it's a 2D problem, we also want our Z-min and Z-max surfaces to be symmetry. However, if a surface is not set with a BC, it's by default set as symmetry. So I could keep these settings. And I will save. Continuing to inputs, we will solve for equations in the Navier-Stokes equations with pressure and only U and V for a 2D problem. We do not need any further models or properties. However, reference properties is one interesting feature to provide an automatic calculation of non-dimensional numbers, such as Reynolds number, Nusselt number, etc. For our phase properties, we can define a name with some properties similar to that of air. Or alternatively, we could have loaded air from the material library. Then, phase interactions is not important. It's only valid for multi-phase simulations. Simulation parameters controls how to run the simulation. We'll have an unsteady simulation with a stopping point if the flow time gets to 10,000 seconds, or if we have 4,000 time steps. We'll start the initial time step at 1 second with a maximum number of 20 iterations per each time step. We could choose a fixed time step, which would keep the 1 second for each time step, or we can use adaptive time stepping and allow TransAT to automatically calculate a time step. Under these settings, it's controlled by the CFL limits. We'll set a range between 0.5 and 1.0. Therefore, based on the flow velocity and grid size, as a larger CFL number allows for a larger time step, we'll keep it at 1. We also need a coefficient or a control based on the diffusion, which we'll set between 0 and 2. For auto relaxation, we'll define 0.83. This automatically sets relaxation coefficients as the equations are solved. Under equations, we'll first define a convergence tolerance. Within each time step during the iterations, the time step will be converged once a tolerance of 1e to the negative 3 is reached. We can leave the remaining settings as default. Under initial conditions, we need to define the values of the variables at the beginning, at the 0th time step. Then, for u velocity, we'll set the entire domain the same as the inflow velocity, and the v velocity to 0, as well as pressure to 0. Under output management, we can keep all of the default settings, just ensuring that we output to bare view every 100 time steps. And under geometric series output, we output initial results every doubled time step until we reach 100. Otherwise, we can also keep non-dimensionals to calculate Reynolds number and other non-dimensional numbers into the file ndnumbers.dat, and additionally min and max values into this file. We'll save to keep all the settings of our setup, continue to the Execute tab, and we would be ready to start the simulation. However, we just showed the basic workflow for the cylinder template. In the following videos, for the basic mesh or the standard mesh and the BMR or block mesh refinement, you can view how we could set up different meshes to solve the same problem differently. Otherwise, I'll make sure it's saved and close TransAT.